Hello, welcome. Oh, forgot to put my face in there. Hello, welcome. How's everybody doing today? Hope we all had a great weekend. Ready to get back into it with more real-time multi-user networking, at least a few more slides of that before we move on to our next topic. Now remember, we have an exam on Friday. Got an exam on Friday, and it will cover a little bit of this stuff. So if you've done the homework, that should help you out pretty tremendously. If you understand how to implement TCP in Java, how to transmit keyframes, deltas, object serialization, and then this next topic that we're going to look at after we're done with deltas here, the scanning topic, you'll be all set for the exam on Friday. When we left off, we were looking at client-side interpolation. Client-side interpolation. Someone asked what the exam format will be. It'll be pretty much the same thing as last time. You will have a task to complete, and hopefully there are no issues with my deployment of it this time. I'll actually make sure that I do it manually, so that won't happen again. And otherwise, if the network crashes or it isn't able to be completed for some other reason, well, that's always a possibility too. So I'll think of some contingency there. Okay, so what happens when you have client-side prediction? So if you have a network approach where you're sending deltas between keyframes, and then the client has to wait for a delta or a keyframe before they can update their state, well, that usually ends up with a pretty noticeable lag on the client side. And if there's one thing clients don't like to see, it's lag. So clients will try to predict deltas on their own. So they will try to simulate the update to the state that happens based on their input. I say that this is common in video games, but it's actually the field of client-side prediction is largest in video games because it's the most complicated problem, because simulating video games is complicated. But almost every network tap has some kind of client-side interpolation. Even some of the really simple ones you've written have some fairly rudimentary stuff, like when you click a button, the button gives you some feedback that it's been clicked without waiting for the server to acknowledge that the button was actually clicked, and then whatever happens, happens. So that's kind of a form of interpolation there already. But you see a lot of that in web apps where you will click a button and then something will happen, and then you will be brought to whatever it is that the state change actually is. So you'll click a next button and some stuff will happen. So a lot of the time, instead of actually interpolating, what they'll do is they'll put in a load screen or a transition or something to give the client some immediate feedback about what's happening. But in games, we don't want to see load screens or something when we're waiting on our inputs to be reacted to. So we actually try to simulate what happens when your input is reacted to. And this is also done in live video and different things like that. We try to simulate what will look like in the next frame. And this effect is called interpolation. So clients will verify their predictions against the actual deltas after they got them. So clients will try to figure out, okay, what's the state going to look like based on my understanding of the user's inputs. Then the server actually gets the inputs, processes them, and figures out the true state. And now the client gets that information, and then they have to update their state to match it. And that's when you get things like rubber banding or rapid rewinds in the case of your video, is when the prediction doesn't match the actual outcome that the server computes. So in this case, we say that the server is authoritative because what it says goes. So once a client gets the server's interpretation of the state, it must revert back to it. And that means that whatever it predicted, it has to undo, has to basically go back in time and then update it to whatever the server actually tells you happened. So if you're rubber banding a lot, That's pretty much why. Now, the interpolation thing was more important when latencies were higher. As latencies have gone lower and lower to the point where a 40 millisecond round trip is relatively normal, this will be less and less required, which is good because it's a very complicated thing to work with. So as latencies go down, it's possible to just wait for the server's next delta or the server's next keyframe and not have to do this kind of interpolation, which is much easier for you, the programmer, and also a little bit better for the user in most cases because they don't have to deal with that rubber banding. And because, again, interpolation is a complicated thing, it also adds to the complexity of the program, can cause many other problems besides that. Now, deltas are used all over the place. They're not just used for your real-time networking interactions and things like that. I think last time somebody mentioned like delta backups and all that sort of thing. Yeah, those are deltas too. So if you've ever worked with version control software like Git, which obviously is used by things like GitHub and GitLab, Git stores your changes as deltas. So if you push a change to a branch, it will store the branch and then your change as a delta. And in order to compute sort of the finished product, you get the branch plus the deltas. That's the finished product. So that avoids you having to resend all of the files every time. It would be really, really difficult if you had to resend and re-download all the files every time. And so Git has this very elaborate system of change tracking with the base file as sort of the root of those changes. And then you've got your backups and your version archiving, same thing. When there's a small change to a large file, you just have a delta stored, and then you can build the new file based on the original plus the delta. Application updates are often delivered this way, so if you have a game or some other application that's like 60 gigs, most of the games are that large, right? But then there's also things like Photoshop or CAD or things like that that are also relatively large. When those applications update, you'll notice you don't have to download a whole 20 gigs or whatever again in order for them to update. They only update a small file, hopefully. Some software is not set up to do this, and that's obviously very annoying. But hopefully they download a small file, and then they patch themselves with that small file, so they don't have to download the entire application over again. They just download a delta and then patch themselves with that. You'll see interactive web pages using delta sometimes, but it's honestly it's less common on the web because it's kind of a pain to do anything in JavaScript, I guess, and I don't know, web just doesn't tend to get these kinds of technologies as often as everyone else. I don't know, that's just sort of the way it is. So typically you'll see when a web page requires you, like let's say you have a really interactive web page where there's like a previous and a next button, and that takes you to another version of a fancy web page. If they were clever, they would download the sort of skeleton of the fancy web page, and then when you hit next, they would only download what is different, just the filled-in content. But you rarely see that. You usually end up with the entirety of those contents being re-downloaded, unless they have something like a frame inside of a frame. But that doesn't count. I mean, when you load the next page, they typically don't recycle the parts from the previous one, which is unfortunate. So if you're a web developer, try to do that. It is helpful to your user base. And certainly there are websites that do that. It's very useful, especially because it saves your users a lot of bandwidth, which means it saves you bandwidth in terms of not having to deliver it to them. You also get database updates in general. So if you have like an SQL database and you are trying to push a new line to it, if you're trying to update it, well, you're obviously not pushing a whole new database, right? So if you think about it, most of what is updated over the network is in a delta form. We very rarely send the entire content of the information. So even when we're updating like a database of stuff, we are pushing generally deltas, just changes to the database. And likewise, if you're reading from the database, you probably only get the changes since you last refreshed it. You wouldn't refresh the entire database, or that would be a separate command. So that brings us to the question of when to update clients. I'm not going to pull up the color grid implementation here, so you can just take my word for how this is done. But in color grid, if we have 4 clients connected, and right now, let's say we can send 7,500 bytes. So right now we're sending 13,000 or so. So let's say we've reduced it a little. We got it down to 7,500. We did the whole converting colors to 1 byte things. All right. So still, we have 4 clients at 7,500 bytes each. That's 30,000 bytes that we have to send to do a single state update. If we do that 32 times a second, that's a tremendous number of bytes per second. If we send all those 30,000 bytes at once, so if we update all of the clients at the same time, well, that gives us a tremendous spike in networking activity. We have to send a 30,000 byte burst, and then we do nothing for a while, and then the next keyframe rolls around. We send another 30,000 byte burst. That would be very spiky, and we don't want to do that. We want to use our resources consistently, especially our networking resources, because if there's a spike in networking usage, that increases the odds that you're going to fill up a buffer somewhere and something's going to get lost. So what the current color grid implementation does is that it has the keys being sent asynchronously. Each one of the worker threads sends keys on its own timer. So right now it has its timer, it ticks every 32nd of a second, so 1/32nd of a second, 32 ticks a second, and it sends a key every 1/32nd of a second. But it's not synced up to a master clock. Each thread keeps its own timer. This means that with that implementation, it's essentially impossible to send deltas because you would have to compute the delta for each client, right? So that's the biggest downside of doing it this way, of doing it asynchronously. If there is just one keyframe that is sent to all clients, then you can also compute one delta for all clients. Whereas if you do it asynchronously, the way it's done now, well, then you would have to create a new delta for every client when you update them. That'd be really difficult because you'd have to figure out, well, what was the last key that I sent them? What's changed since then? It would be really quite complicated. So if you're going to do the bonus, you'll probably have to fix this functionality so that all of the clients get the same key. So you could do that in a number of ways. You could still have them transmit asynchronously, but they could transmit a key that they pull from the color grid at a regular interval. Okay. Or you can have them all transmit synchronously so that they're all synced to the same clock and all of the threads send out at the same time. But again, that leads to the problem of having spikes in your networking activity. There's also the problem of everything having to be thread safe when you do it this way. If multiple threads can access the state at the same time, that could cause problems. There are many reasons why this is not always possible or necessarily a good idea, but it is the easiest implementation and it does have its advantages, so that's why that's the way it's done in the current implementation of your homework solution. So you might want to think about how you can make it a little better. And now let's talk about Discord for a bit and how Discord manages to handle the truly amazing volume of real-time traffic that it handles. So Discord uses UDP primarily. It has a control channel and a voice channel, so it has multiple different places where you're connected at any given time. So it's not all just going to one port together. It's actually multiple different connections. It uses the Opus audio codec, which is a way of compressing your audio. So we were talking about how to compress a 50 by 50 grid of colors. We obviously haven't talked at all about how to compress something like an audio signal. There are tons of different algorithms for compressing audio out there. Opus is one of the newer and supposedly better ones. I've definitely had a lot of different audio codecs over the years on Vent and TeamSpeak and Mumble, and Opus sort of eventually superseded all of the older ones, so presumably it's better because it has taken the place of all of the others. Discord uses Salsa 20 encryption, which is a cryptographic algorithm that is best known for its speed. It became very popular when Google announced that it would begin using Cha-Cha 20, which is a successor to Salsa 20, as one of its primary encryption methods. So I'm assuming Discord has probably also moved to Cha-Cha 20 since that announcement. It's possible they're still on Salsa 20. I believe the main difference between them is the Cha-Cha 20 is a little bit even more performant. Neither of these have had any serious vulnerabilities against them in quite some time, which is a good thing. Every cryptographic algorithm has its challenges, and I'm sure both of these have as well, but nothing particularly serious has gone wrong with either of them. When you join a Discord channel, it exchanges only a few thousand bytes of information, so different things like your encryption keys and all this other stuff is negotiated. A little bit of other trivial setup, but you'll notice that when you join a Discord server or a Discord channel, everything happens quite quickly. There's really not that much networking setup to be done. And where Discord really gets its power and its ability to handle so many clients simultaneously is that Discord only acts as the relay for the voice traffic. Your voice is compressed and encrypted almost completely on your client, so on your machine, and then it gets transmitted to Discord, and Discord merely forwards it along. So Discord behaves something like a router. But it's a little bit more complicated than just being a router, because Discord basically creates these channels, these sort of boats or groups that users are put in, and those correspond to the voice channels that you're in. And when Discord receives some voice traffic that's bound for a group, it has to forward it to every person in the group, right? So in addition to your voice being encoded into the traffic, we also have to encode that group information so that the relay servers know where everything is going. And when you transmit your voice, let's say you're in a channel with 20 people, if you speak, your voice goes to Discord, and then Discord propagates it out to 19 people. This makes it so that you only have to send one connection at a time. You only have to send your voice to Discord. Discord does the heavy lifting, which is the transmitting it to those other 19 people. This is one of the problems that we see in the color grid server, is that it has to send its data to every one of those clients personally. So Discord takes on that role as well. It takes on the role of sending your data to all of the clients personally. And you see that the clients in Color Grid are similar to Discord clients, where they send their data only to the server. They're not in charge of updating all of the other clients. So this is a client-server model with no peer-to-peer connection. One of the biggest perks of this versus the old way some programs did it, like I believe Skype for some time did it, is that you don't expose anybody's IP. So everybody's just getting messages from Discord and sending them to Discord. Nobody's getting messages directly from anybody else. With those old algorithms, when you exposed your IP, you would invariably get trolls that tried to DDoS you, especially when you were trying to have a good time and play some video games. You would get DDoSed by angry people once in a while. So it's nice that IPs aren't exposed in voice chat anymore. Now, Discord transmits audio. You can change this in settings, but it's between 30 and 64 kilobits per second. I think the default is closer to the 64 end. The 64 end, well, if we divide that by 8, because that's in bits, we want bytes, that's 8,000 bytes per second, right? That's not really that many when you consider that we're struggling to send 7,500 bytes for just a crappy 50 by 50 grid of colors, right? I mean, that's very impressive that they can transmit a full, clear, crisp audio in less, well, just slightly more than what we're using on our stupid little color grid application. And they don't send this by the second, obviously. You want your audio to be much more real-time than that. So it's actually broken up into about 50 smaller packets per second. So those 8,000 bytes are spread out over 50 packets. You should notice that they're not full, obviously. It's 8,000 divided by 50 is nowhere near the max size of a segment or a UDP datagram. So they're basically sending them quickly so that you keep getting that real-time element to them. It's similar to what you've got to do for your color grid execution too. You've got to send either after so many, for the deltas bonus, either after so many state changes have happened, so after so many updates have occurred, or after just some time has expired. So you still want to be able to send data very quickly, even when there's not a lot of action going on. And Discord's likely the same way. If somebody speaks and then stops, it will still send data, even if it doesn't have a full packet's worth of data to send. It samples on your local machine at 48 kilohertz. So for you audio people, that's pretty much like DVD quality audio. There's what people call like DVD quality audio is typically the highest you'll get on your computer, unless you're a big enthusiast and you have like specialized equipment. You'll typically just get this 48 kilohertz sampling rate, and that's obviously 48,000 times a second. Remember, an audio signal is just a analog waveform or a series of fancy analog waveforms that are usually plotted into this cool little histogram of different intensities, and you just want to take one slice of that and send it along. Well, obviously, if you're doing this 48,000 times a second, but you're only sending 64,000 bits, And of course, it takes more than 1 bit to send an audio signal. It takes quite a few. Well, you're not sending all of the samples, right? So the Opus codec and all the other codecs like it have to figure out how best to take the samples from your host machine, which are coming in very, very fast, pack them up and compress them and get them out on the other end in such a way that is clear. So it's a very complicated challenge. One of the cool things Discord does to save bandwidth is it'll send nothing during silence. It'll just send keep alive kind of heartbeat signal. So every second or so, it'll transmit what we call a heartbeat in order to let the server know that the connection is still alive. So remember, it's UDP, so it's sessionless, so we wouldn't know that the person on the receiving end is still there. The server gets a heartbeat from you, it knows you're still there, even if you're not speaking. In order to pull that off, you have to, and you can think about this logically, you'll realize that you need to do this. You need to send some sort of stop flag when someone is done speaking, and then a start flag when somebody begins speaking in order to tell the server to start listening again and send the traffic back out. So when you stop speaking, it sends out a stop, and when you start, it sends out a start. And this corresponds pretty well with the voice over IP model, where you have like this voice activated or push to talk signal. You just transmit the start and stops when the activation starts and stops. And this gives Discord a lot of power, a lot of information routed. During peak hours, Discord routes over 1 million concurrent voice calls alone. So concurrent, like at the same time, over 1 million voice calls alone. Over 220 gigabits per second, so a tremendous amount of web traffic. That's the equivalent of 220 fiber lines. This is for their global operations, and it's probably much, much larger today. So that's not all going to one server. Discord has servers all around the world, has at least 3 in the United States. But that's still the equivalent of 220 gigabit fiber lines, and that is quite impressive indeed. And over 120 mega packets per second. So remember, the packets are not as big as they could be. They are usually quite small because they're sent quite often. So you're looking at millions and millions of packets going out every second. And of course, people get angry at their voice chat and at the people in their voice chat. And people like to take out their rage at servers they don't like, especially in a difficult political climate like the one we have today. You don't like a candidate? Well, go DDoS their Discord. That'll show them that you win politically or something. So you'll see a lot of DDoS attacks on Discord. Anything where people can communicate is usually exposed to a lot of DDoS. So if you build any kind of platform where people are allowed to interact, they will inevitably attack each other because haters gonna hate, right? And Discord is able to handle those fairly impressively without going down. If it detects DDoS, it just migrates your server over. So sometimes you will get some temporary degradation, but generally speaking, when your server is being DDoSed, you don't even notice. And all of that is before even considering the fact that Discord allows you to stream and send video now. So this is just for voice. So very impressive that they're able to do all this, and that all comes down to good real-time networking, which is very difficult to do indeed. Now, other things to think about in real-time networking, which we haven't addressed yet, is how you can pull it off when you're in a peer-to-peer model. So if you don't have a primary server, we've talked about how you can do it if a server computes state. What if every client has to compute their own state and also exchange that state with every other client? This is one of the major reasons that peer-to-peer is so difficult, and especially difficult for real-time, and why there's almost no real-time peer-to-peer sort of applications out there, because it's just too difficult to do. And this is something to think about when we get to some kind of peer-to-peer model, is how you can make it real-time with all the clients exchanging data with every other client. One thing to think about is that as more clients join the network, the amount of work for each client grows and grows, and it grows very fast. So when there are 4 clients, you've got to update 4. When there are 5, you've got to update 5. Every time a new client joins, it puts more and more burden on every single client. So it's a multiplicative burden. And your overall burden on the network also scales in proportion to how many clients there are. So when one client joins a set of 4, every single client now has an extra workload of 1. So you've added in total the 1 extra workload to the 4 original clients, plus 5 more for the new guys. So you've added 9 clients worth of workload to the network overall. Again, it scales very quickly. When one person joins, you've added 9. When the next person joins, you've added like, what's that going to be? 5 plus 6, yeah, so 11 more. Yeah, the next person adds 11, and so forth. It gets very, very large, very fast. One thing that you can do to avoid ever having to transmit state is to program deterministically. And this is used in many older strategy games, real-time strategy games, so this was the way it was done in games like StarCraft and Age of Empires. This is how those games were able to be real-time and so technologically advanced sort of ages before other games of their type were. And this was also used in some early shooters and early fighting games, but those games are notoriously bad for latency purposes. So like the original Quake and stuff would be very difficult to play by today's standards because this is not a great approach for latency. The best known example of this kind of deterministic programming is called Lockstep. And in Lockstep programming, what you do is this: there is no randomness allowed. And that's because every client has to be able to simulate the entire state locally just from initial conditions and inputs. So given that you know how the state started, and given that you know everybody's inputs and exactly what time they came in on, you can simulate the state now. And you do this without any key updates whatsoever. So you basically start with an initial state. You get all of the inputs at fixed timestamps. Everybody has to agree. So we have to establish a consensus that we've all gotten the inputs before we advance. And then we advance the simulation. All of us advance the simulation one more interval locally on our machines. If there's a desync, the game is broken because something different appears on your machine than on my machine. That's pretty irreconcilable because I'm going to start sending things that don't make sense logically to you. So typically that's going to break the game or require everything to be re-simulated. The big advantage is that we never have to exchange state. We just exchange inputs. So this is very difficult to implement. And the problem with it is that in order to establish that consensus, you need to make sure everybody's gotten all of the inputs for that time interval and everybody's confirmed it. That means that your game is only as fast as your slowest person, because however long it takes the person with the worst ping to establish the consensus, that's how long everybody else has to wait. No one is allowed to advance the simulation until everybody has agreed on the next set of inputs, and so you are bound by the performance of the lowest performing client. That's why this was especially ill-suited for early shooters and that kind of thing when everybody was on good old dial-up. All right, that concludes our look at real-time networking. And next we are going to check out port scanning. Let's see, where is this thing? Here we go. We're going to check out port scanning, reconnaissance, all of this wonderful stuff. And we are going to do that with a tool called NMAP. I'm going to lead with the installation and brief little looky at NMAP before we actually move into the slides and everything about it. So I'm just going to show you where to get it and all that stuff before we move on to it, so you can maybe play around with it while I'm talking, and then we'll do some more playing around with it on Wednesday. So I'm here in the VM. You're going to need it in the VM in order to do the exam, most likely. However, you can also install it on your home machine. It has a Windows and a Mac and a Linux version. But just remember, you will need it in your VM, so you may as well. And let's first look at where to find it. So if you search for NMAP, you will find the nmap.org as your first result. That is what we're looking for. So we're looking for nmap.org, and we're looking for the download page. I'm going to go ahead and link this in Discord so that we are all on the same page here. So I'm going to link the main site, and then obviously the downloads page. Not difficult to find, but hey, I'll link it anyway. So we've got NMAP, and we've got the download page for NMAP. Okay. Trippy. All right, so I am on the download page here, and you see a lot of words, but most of you are probably looking for the Windows binary. There are a few Mac users here. Let me see what the Mac users can do. Well, you should be inside the VM anyway, so that's not a problem, but you've also got your Mac instructions here. Yep, yeah, you got your map instructions. Now, it is intended primarily for Linux. It started as a Linux application, but I don't think we have a lot of Linux users in this class, so you'll just have to deal with the Windows one. And the nice thing about the Windows version is it comes with this neat little graphical user interface, because they assume that Windows users are idiots and they don't know how to use the command line, which is probably true. Windows users are pretty command line averse, and so this wonderful user interface thing is quite useful. All right, it's this NMAP 7.91/setup.exe that we are looking for here. All of you should have admin rights on your VMs, so you can install this without issue. I've already downloaded it here, and I've actually already installed it, but I can show you the setup again. Okay, I agree. Lovely. Now you can install all of these different packages. I don't think you need all of them. You probably don't even need npcap installed, because Wireshark probably already did it, but it doesn't matter if you do or you don't. So I left it checked and I reinstalled it, and that was fine. I think Wireshark actually might have a more up-to-date version, so there might be conflicts, but give it a shot either way. The default install location is fine. And then it'll ask you after a certain point in the installation whether you want to install NCAP or not. You should. It'll ask you if you want to install the Wi-Fi version in the checkboxes, so the 802.11 version. You obviously don't have to if you're on the VM, because the VM doesn't have Wi-Fi. Otherwise, by all means, if you install it anyway, it doesn't matter. It's quite small. So again, don't worry about it. And I tested Wireshark after this install, and it does seem to still work correctly, so I don't think I messed up my Wireshark install either. And in fact, I will open up Wireshark so that we can see what happens when I am running NMAP. So I will hold off on moving forward here until we are set. I will go into the slides here while you try to get it downloaded on your VMs as well. Okay. Whoops. You can tell we are getting far in the semester when my desktop turns into a mess. The further we get, the worse my desktop becomes. If you've got any problems downloading it, let me know in either chat, and I will see. Preferably with a screenshot included as to what your problem is. So, we're kind of at the halfway point in terms of the content. We've pretty much finished looking at all of the just plain networking knowledge that we need in order to start getting into some of the cybersecurity stuff. So we know how to do TCP and UDP. Unfortunately, we're pretty limited by Java, so a little bit more on that later. But we've got most of what we need to get into the cybersecurity stuff, and so now we're going to start basically that phase of the course. So we've already begun a little bit of that with the red-blue challenges, and now we'll just sort of ramp up more on that front, the trying to break into these little applications that we've been able to write. But again, the goal of this course is still to focus on you as a developer, so we'll mostly be writing code and then figuring out how to break our own code based on the poor networking standards that we put into it. Alright, so the first step in any cybersecurity attack, or at least most of them, is to do some sort of planning, and then to do some sort of scanning or reconnaissance. So let's look at planning first. A good hack always begins with planning, especially the kind that you plan to do legally for money. So if you are going to hack somebody legally, that is, that you are paid in order to conduct some sort of cybersecurity test, there will be extensive planning. So if this is a profession that you think you want to go into, if you think you want to go into cybersecurity, expect to be the kind of person who is careful and writes a lot of documentation and has a lot of ideas and a lot of meetings before they ever touch the keyboard. There's not a lot of let's just fuck about and see what we can do in paid cybersecurity. It is a very meticulous and well-documented process because you don't want to break anything unintentionally. That's the primary reason. If you break something unintentionally, you might still be held liable for it. So some of the things that you want to think about when you're in this planning phase is what or who in that organization might be vulnerable. What kind of people at that organization have the goods? Like, who's got the encryption keys, the important stuff? Who has the private server encryption keys at John Carroll, for example? Which people do you think have those? There's obviously at least a handful of folks that have access to that information. So somebody like the chief of IT probably has it, right? And then who else? Is there a second or a third? Who's the most vulnerable person that might have that kind of information? Where might that information be physically? Like, what server is it stored on? What are we even looking for? What kind of info would be useful? Do we want the private keys to, I don't know, the web server or something like that? I mean, what kind of stuff is valuable or vulnerable at that organization? What do we want to accomplish? A lot of the time, if you're doing it legally, what you want to accomplish is something that's described to you by the client. They want to know how they're vulnerable in some particular aspect. Although a lot of the time you'll get more broad order to figure out where you're vulnerable in all departments. What are the victims' capabilities? Are they going to be able to avoid detection? Do they have some sort of capability to deal with you once you've intruded into their system? What's their security going to be like? What can you learn about them without actually interacting with them at all? So in the planning phase, you're not going to be sending anything to the victim or going out and looking at their site or anything. You want to be as under the radar as possible. So perhaps you search for them on the internet and figure out what sort of thing they're into, what their building might look like, anything that you can get publicly. I think that's still considered part of planning, although some people would lump that under the next phase, discovery. And how can you avoid detection? So what can we do to the client that helps us avoid detection, get away with the goodies? All of the above is often documented in detail and presented to the client at the end of any kind of cybersecurity action for money again. When Red Team plans what they're going to do, and typically when we attack a client for money, this is called penetration testing, so usually shortened to pen testing. Pen testing is a service where an ethical hacker, a red team, attempts to break into a network or some part of a network. Okay, so when I talk about pen testing, I mean a group of hackers who are permitted to test a network attempting to break into it legally. And in addition to the stuff in the previous slide, there's a lot of other things to discuss. There's your contract write-up, and your contract write-up is usually pretty extensive. You've got your scope of targets in there, your scope in terms of the network and the physical area, the allowed targets. Often there are a lot of methods that are off limits. Obviously, when we're pen testing a network, we don't want to do things like extorting employees at gunpoint. That's going to be off limits. And usually there's some kind of language in the contract to indicate that. But typically, minor felonies are on limits. So things like breaking and entering with no property damage, following people in, accessing areas you're not supposed to, felony trespass, all these kinds of things. Most of these don't extend into felony range, but in some cases things like picking a lock would be considered breaking and entering, and those are often within scope of the pen testing agreement. So the client agrees not to prosecute for those things too often. And of course you have your pay structure. Typically you are not paid by the amount of vulnerabilities that you find, which means that in order to be a cybersecurity company that generates fair income and is able to survive in the financial world, you have to have basically a reputation for being able to find stuff. So you get your flat fee or an hourly fee or a fee based on the amount of time that you spend attempting to pen test, and then it is your reputation that guarantees that if there was something there, you would have found it. It would be a bizarre incentive if you were paid per find. There are other elements of the cybersecurity industry where you are paid per find. There are things like bug bounties where hackers are paid for every bug that they find in proportion to how serious it is usually. Those definitely have their own problems, but generally in a pen testing agreement, the pay structure is some sort of flat fee or hourly fee. Almost always set a time limit and a frame of times that the red team is able to attack. You might say this gives blue a very good opportunity to prepare themselves, and in some senses it does. A lot of organizations will attempt to put their best foot forward and sort of update all of their stuff and get their network as ready as it can be for that time frame, while others will try to sign these agreements without their IT department's knowledge in order to test them in their most unprepared state. That's usually the way you want to do it. You would rather test them in an unprepared state because that's what's going to happen if an attacker actually comes at them. That said, you still want to set time limits. You don't want to give the red team months to do what they're going to do. And you want to know what days they're going to do what they're going to do so that if the network is somehow accidentally destroyed, somebody in charge knows why and is able to quickly get it fixed. So if you know that the attackers are going to be doing their business on a Saturday in June and your entire network goes down on a Saturday in June, well, you know why. You don't have to panic and call the FBI and all that stuff. So it's helpful to have time limits for that reason. You would just call your red team, make sure that they did it, and then get it fixed as quickly as possible. So you also generally have a list of contacts and then some sort of policy on how all of the information that's collected is going to be reported. So this is obviously what the client is paying for, right? The report that's generated at the end that shows them all of the things that have gone wrong in their system, how to do it, what kind of information is going to be included there is usually in the contract. So the fact that they're going to tell you not just what they did, but the entire chain of events that led up to discovering that vulnerability. So everything from the planning phase to what the hackers tried in order to get to the idea that they have to do this particular thing, all of that's going to be included in the final report. And this whole kind of set of terms and everything in hacker terminology is usually called the rules of engagement, so kind of a reference to war games and that sort of thing. You know, it's whatever. It's a little bit of a grandiose phrase, but yeah, it's a rule of engagement. It's an adversarial relationship between two teams. At this point, it's standard practice for the client to issue what's known in the industry as a get-out-of-jail-free card, and these are typically in writing with the contact info of the people in charge, people who have the authority to say, please do not arrest this person, they are authorized to attempt to break into the building. And other kinds of indemnification too, so if in the event that when you're picking the lock you break it, typically there is a small amount of damages permitted as part of the penetration testing agreement. By small amounts, I mean they don't want you to smash windows or demolish servers, but if you had to, I don't know, cut an Ethernet cable or something, that would probably be more in the realm of acceptability. If you damaged a lock while picking it, that would probably be more in the realm of acceptability. Again, it's up to the individual organization. Some would say no damage at all, you're not allowed to damage anything. That's also very common. But in either event, everybody who is involved on the red team needs to get issued one of these get-out-of-jail-free cards in case they are caught and the police are called. They certainly wouldn't want to go to jail. So let's talk about Coalfire Labs versus the Iowa Judicial Branch. So in 2019, Iowa State Judiciary contracts Coalfire Labs, which is a cybersecurity firm, to pen test their systems. And they agree, in addition to a digital pen test of the network, they also agree to a physical pen test at 3 different locations. And because of a mix-up in who is authorized to issue a pen test, the hackers that work for Coalfire that did the physical pen test ended up being arrested and spent some time in jail because their get-out-of-jail-free card didn't work. And the crux of the problem is that the state contracted them to attack these 3 buildings owned by the court system. One of those was a county court. And the county said, well, the state doesn't have the authority to allow people to break into our court because the county has sovereignty over this court. So we're going to put you in jail. So the moral of the story is that if somebody gives you permission to break into a building, make sure that they have the authority to give you permission to break into a building. Not to belittle Coalfire or anything. I'm sure it wasn't their fault in the slightest. I'm sure it was just a stupid mix-up. But another point that needs to be learned from this is that if you do want to go into this field, if you do want to be an ethical hacker, and you want to do physical pen testing, which is a very fun part of the job, I'm sure for many people it's something that's very appealing. If you're going to do physical pen testing, do be ready to spend at least a couple of nights in jail. This is very risky when you are a penetration tester, right? Because if you do get into legal trouble, if you do have a criminal record, you will likely lose your job because it will be impossible for other organizations to trust you. So it's very difficult to continue working in this field if you have a criminal record. That means you have to be very careful about not doing anything wrong. You can also lose clearances. A lot of the organizations that order pen testing order it on the basis of some clearance that you have or they have or both. And yeah, the moral there also is, if you're going to do this, live a otherwise clean life because you kind of need to in order to be in this industry. Let's look at that report though. Let's see if we can find some interesting details in that rule of engagement. So, first thing you'll notice is that because the American government lives in the future, why do we have this, by the way? Why do we have this agreement at all? Isn't this private? Well, no, because a government entity contracted this. It's subject to public disclosure. That doesn't mean they have to disclose it in what is likely its original PDF format. The government, in typical fashion, used like black whiteout, real physical black whiteout, and a scanner in order to upload it. So typical local government fashion on that. Hilarious. All right, so let's read the purpose here. The penetration test and corresponding risk assessment will be performed by Coalfire to test the adequacy and effectiveness of security control measures in place to protect the security and integrity of sensitive information technology, IT systems, and data. So this is a rules of engagement, again, that's what they're calling this document. Coalfire is under contract with Iowa Judicial Branch to deliver a penetration test, which they call the project from here out, etc., etc. Okay, and then they've got a few default boxes that they can check, so this shows you some of the industries that penetration testers often work in. They've got their PCI DSS compliance, their HIPAA compliance, financial sector compliance, federal public sector compliance, SOC, utilities. So there are all these different compliance entities that these cybersecurity firms will often test for, so to make sure that you're in compliance with one of these specific organizations or specific standards. Or they can do what's called here a securities best practices, where they're just testing the general security of their system. So they've specified some of the stuff they're doing. This is like an order sheet against scope, right? So the scope here is they're going to do an external network penetration test. They describe this in more detail later, but of up to 200 IPs on the network. Then, if they can gain internal access, they'll do an internal network penetration test. If they don't gain internal network access, then they'll move on to what they call an assumed breach attack. All right, and then there's some more details in an appendix later on. They're going to do a application penetration test on 3 of the web applications that the court uses. And then they're going to do some social engineering stuff. One of the social engineering things is spear phishing. Remember we talked about that earlier. That's phishing, but on an individual person. So they're going to try to collect background info, probably browse the social media of specific employees, and then attempt to spear phish them that way. They'll do a pretext phone call on employees, see if they can get them that way. And then the part that's interesting to the story, the physical security assessment. They're going to attempt to gain physical documentation at 3 different locations. That is to say, they're basically going to try to steal documents. This can be during the day or evening. They're going to try to talk their way into areas where you're supposed to have limited physical access. And then they're going to attempt to physically gain internal network access, so by plugging something in to one of the machines. A common expression in cybersecurity is that physical access is total access. So if you have physical access to a machine, generally speaking, it is completely yours to do what you will with. All right. Okay, so next time we will look at using NMAP to perform some of this scanning stuff, and we will look at the rest of this scope document as well. So I will see you guys on Wednesday. Please make sure that you have NMAP installed on your VM. If you've got it done successfully, you can open up ZenMap, and it's going to look something like that. So if you've added it to your start menu and everything, it's going to be under N. It's going to be under NMAP, and you go to ZenMap, and it's this lovely not command line tool at all for us dummy Windows users. Someone asked if the requirements were changed. If you mean the requirements for these rules of engagement, no, this is the original that they signed for the court system. What happened ultimately was a miscommunication. So this Dallas County courthouse is actually the one where they got arrested. Dallas County argued that the state of Iowa was not able to grant permission for people to break into Dallas County's courthouse. But more on that next time. So I will see you guys next week. Wait, Wednesday next week. See you guys Wednesday.